I guess we can start. Good evening and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Evgeny Khorov. Evgeny is the head of Wireless Networks Laboratory at the Institute for Information Transmission Problems of the Russian Academy of Sciences. Evgeny also is also head of Telecommunication Systems Lab at Higher School of Economics and associate professor at the Moscow Institute of Physics and Technologies. He has led dozens of national and international projects sponsored by both academic funds and industry. He has authored over 100 articles. Currently, he is IEEE senior member and a voting member of IEEE 802.11 working group. He has contributed to the IEEE 802.11ax standard, which is also known as Wi-Fi 6 standard, IEEE 802.11be standard, which is also known as Wi-Fi 7 standard, and IEEE 802.11 real-time applications technical interest group with many proposals. Today, he will share with us his vision on the future of Wi-Fi networks from the point of view of Wi-Fi standard developer. So, Evgeny, floor is yours.
Thank you, Vyacheslav, for introduction. So, as Vyacheslav said, today we will talk about future Wi-Fi, and this is the first talk about future Wi-Fi, and I will try to provide you some general vision on what happens in Wi-Fi community and what changes in the Wi-Fi standard are coming. So, why we're talking about Wi-Fi? Because 5G causes COVID-19. Of course, this is a joke, and we are talking about Wi-Fi because Wi-Fi today is one of the mostly used technology for data transmission. About half of the traffic transmitted or generated in the internet appears in Wi-Fi networks. The number of Wi-Fi hotspots grows, and it means that the technology of Wi-Fi is very important, and it evolves, and let's see what happens in Wi-Fi community. The history of Wi-Fi starts in September 1990, and the first Wi-Fi standard was published in 1997. Since that time, there were made a lot of amendments to the Wi-Fi standard, which improve its performance by providing high throughput and by extending its functionality. So, from time to time, the 802.11 working group combined together these amendments and published new standards. So we have revisions of 2003, 2007, 2012, and the last revision was published just several months ago. So today we will be talking not about those revisions, those Wi-Fi amendments which are already published, but about those amendments which are currently under development. So they are shown here. And you can see that some of the amendments are already almost finished, and some of them are under balloting, and some of them even do not have an approved draft or even any draft, like these working groups. So let's try to understand what happens with in the task group which develops these amendments, and what will come next. These amendments, the amendments that are shown here, can be classified in two parts. Some of them increase data rates, the rest improve functionality. So let's start with the amendments that improve data rates. Among them, the most important are .11ax, that is also known as Wi-Fi 6, and Wi-Fi 6 is the latest version of Wi-Fi that came to the market. And Wi-Fi 7, which is expected to be finished in 2024. And the work on these amendments has started recently. We also have millimeter wave Wi-Fi, which is again finished at the end of the last year. And we have Wi-Fi or Wi-Fi in light spectrum. And the work on this amendment is going now. And we also have amendment which is for next generation V2X communication. And of course, this amendment can hardly be considered as an amendment to improve data rates. Also, the main differences from this next generation V2X amendment with respect to what is present in the standards, so the first generation of V2X.11p, is improving data rates, improved data rates. So let's start with these amendments and see what are their main features and what happens with them. So we start with the amendments which improve data rates because these amendments, so the data rates is the KPI which is mostly interested for end users. So when we buy this or that Wi-Fi equipment, we try to understand what will be the available data rates. When we're talking about Wi-Fi, we first of all see the nominal data rate, so the data rate that is is supported by the physical layer of this technology. The real data rate will be a bit less, and because we have some overhead induced by file layer or MAC layer protocols, and also we have other protocols that are involved in communication. So the user perceived data rate will be a bit lower. And you can see that from this picture, you can see that from the very beginning, the data rates significantly increased. The first version of Wi-Fi supported only 2 megabit per second. Now we can talk about 250 gigabit per second, this extremely high data rate. And these data rates are improved in several ways. Of course, we have some amendments which adopt Wi-Fi to which add to Wi-Fi millimeter wave support of millimeter wave. And with millimeter wave, we have a lot of bandwidth, and that's why we can easily increase data rates. So this figure, more than 250 gigabit per second, is achieved only in millimeter waves. And today I will describe how it works. So we also have .11ah, which is a sub-1 gig Wi-Fi operating in the low frequency, less than 1 gigahertz. And this Wi-Fi was designed specially for IoT. Unfortunately, right now, we do not have a lot of devices that support this technology. But for IoT, 300 megabit per second is a rather high data rate. So this amendments, this technology can work, can support such applications like autonomous cameras or some other applications which are IoT applications that require high data rates. And as I previously told, we have light communications, and this is ongoing work, and it will support up to 2 gigabit per second. But the most interesting for us is the traditional spectrum, traditional bands of 2.4 and 5 and 6 gigahertz. And in these bands, we have a significant growth in data rates from 2 megabit per second up to 40 gigabit per second in Wi-Fi 7. If you look in the history of Wi-Fi versions, we can see that every new Wi-Fi version operating in the traditional spectrum increased data rates in 10 times. And Wi-Fi 6 or .11ax is the first amendment that changed the paradigm. So it's like an exception, because the increase in the nominal data rates is just 37%, or it can be seen here, but please pay attention that this axis has logarithmic scale. So the increase is just 37%, but the main features of Wi-Fi 6 are related to improving the user perceived data rate, so improving the user quality of experience. And we will talk today a bit more about this technology. And Wi-Fi 7, so from the market point of view, improving just user experience is not good, because you cannot explain to the customers why they need to upgrade their devices. So if people already have devices that support up to 7 gigabit per second, even if they do not use this 7 gigabit per second, it will be quite difficult to explain them why they need to buy new equipment that supports 10 gigabit per second, which is just 37% more. So that's why the developers of Wi-Fi 7 or .11b try to improve both user experience and nominal data rates. So we start with .11ax, also known as Wi-Fi 6, and of course, because of time limitation, I cannot explain all the features which are relevant to this amendment. So for details, please look into this paper, and also we will have a separate talk on Wi-Fi 6, I think, in a month or so. Previous amendments, as I previously said, so before Wi-Fi 6, were mostly focused on nominal PHY data rates rather than on real data rates and real user needs. And if you look at the characteristics of .11ac access point, so it can transmit in theory 7 gigabit per second, but only if the client support very wide 160 megahertz channels. The environment allows us to have 8 spatial streams. The traffic is saturated. It means that we really have enough data to transmit. There is no interference, and the access points and the stations are very close to each other. And in reality, these conditions are very unlikely to occur. This very high throughput is available only in theory, but in practice, we have low throughput. Moreover, today we have a lot of networks operating in the same area, and it means that they interfere with each other. Cisco called interference a silent killer of Wi-Fi communications. Why? Because the solutions which work today will not work in future, where the interference level will be high, because Wi-Fi initially wasn't designed to work when we have so many access points deployed in the same area and so many clients, when the network is very dense. So that's why the developers of Wi-Fi 6, the developers of .11ax, put much effort to improve the performance of Wi-Fi networks in dense deployment. So if you remember, the nominal data rates increased just by 37%. But what are the main features of .11ax? The main features are as follows. So first of all, we have a modified file layer, which improves performance under high interference. We have uplink multi-user, multiple input, multiple output, which allows us to transmit simultaneously several data streams from various stations in uplink. The downlink MU-MIMO was enabled in .11ac, which is Wi-Fi 5. One of the key features of .11ax is OFDMA. Previously, Wi-Fi used only time division, implemented with Coresense multiple access with collision avoidance or CSMA. Starting from Wi-Fi 6, we have OFDMA, which works upon CSMA, but it allows us to transmit simultaneously data for several stations in downlink and uplink using different frequency resources. There are several channel access modifications that improve performance in these deployments, and there are several features, and this is again one of the most important point of Wi-Fi 6. So these features enable and improve spatial reuse. Spatial reuse is very important for dense deployments. Moreover, what we see in Wi-Fi 6 is that the paradigm was again changed from restrict access if it may cause some collisions or if there are some probability that there will be some interference, to allow access and to make the transmission successful and to allow more transmission in parallel. So this is very important spatial reuse. This is a very important feature, and it causes a lot of challenges because this is extremely new for Wi-Fi as well as OFDMA. And right now, we see that this feature is in the standard, but how the devices, real devices that are on the market, support these features. So it's not clear. And moreover, the majority of devices do not support it yet because it's really unclear how to use these features in the most efficient way. And this work is ongoing, and it requires a lot of efforts from both academia and industry because there are a lot of optimization problems there. And finally, there are some methods that enhance power efficiency. So they allow our smartphones to work for longer without being recharged. The next amendment is .11b. And again, you can read this paper if you want to obtain some more details about this technology. So the work on this amendment was started quite recently. And the main, I would say that the main use case for this technology is the virtual reality. So virtual reality applications come to the market, and virtual reality, remote virtual reality requires very high throughput and extremely low latencies, because we need to transmit video with a very high resolution and with very small delays. So as for throughput, .11b modifies PHY to increase the nominal data rates. So it incorporated a higher order of modulation for KCAM. But this significant step in implementation provides us only 20% gain. The order of multi-user MIMA is doubled, so we can have up to 16 spatial streams. And .11b also use twice wide bands up to 320 megahertz. As for, and one more, and I would say that this is maybe the most interesting and the most important feature of Wi-Fi 7 of .11b is multi-link operation. So why multi-link operation is so important? Because so this feature allows us to use several radios simultaneously to transmit and receive. And these radios operate in different channels, so they do not interfere with each other. in the very in some cases. I will explain it a bit later in detail. And what is important is that this feature allows various vendors to compete with each other. Why? Because if you have like .11ac standards, we have some KPIs written in the standard, like it supports up to 7 gigabit per second. And so if the device really supports this modulation encoding scheme, so the vendor can write on the box that, okay, it supports up to 7 gigabit per second data rate. And if we have two devices, we see on this box that 7 gigabit per second, so they both support 7 gigabit per second. We cannot understand which device to buy, because this is only like this KPIs come from the standard, and the vendors have no opportunity to increase them. If we are talking about multi-link operation in general, we can say that, okay, one device can work only in one link, but another device can work, supports 2 links. The third device supports 3 links, and so forth. So it makes KPIs different. KPIs of various devices different, and so the customer can make a choice because it has different different performance. Multi-link operation is much easier to implement than, for example, a MU-MIMO, because there are really a lot of issues with implementing a MU-MIMO with 16 spatial streams in a wide band, because we need we have a lot of overhead caused by channel sounding. And the overhead is so huge that it diminishes the gains that are provided by high-order MU-MIMO. In contrast with multi-link operations, so we can just combine together several radios and obtain very high throughput. So if we are talking about nominal data rates, so at one link, we can have up to 46 gigabit. Sorry, this is a mistake here, not megabit per second, but gigabit per second. We can have up to 46 gigabit per second. And since we can have several links and we can operate in several links, the nominal data rate is n times higher. Multi-link operations cause some issues because I previously said that we can simultaneously transmit and receive at various links. Actually, this is not always true. And sometimes, so it depends on the devices, it depends on how the channels are aligned. So whether they're whether they're adjacent channels or they're separated by some frequency, they're separated in a frequency domain. And if we if we can simultaneously transmit and receive, we can implement a synchronous multi-link operation in which we can have just a wide pipe to transmit data. But if we have the interlink interference, we need to synchronize transmission at various links, and this causes a lot of challenges. And sometimes this really happens, and there are a lot of solutions in the spec that allows us to organize such a synchronized multi-link transmission. Another important novelty of .11b is coordinated operation in neighboring networks. So typically we have a lot of access points deployed in the same area, And .11ax or Wi-Fi 6 try to solve the problem of inter-network interference in a distributed way. So just by modifying channel access rules and improving spatial area separation. But .11b introduces coordinated transmissions. And such type of, there are no clear solutions that are put in this as a standard yet, but there are some ideas that have already been discussed in the task group, and they're related to coordinated scheduling, coordinated ODMA transmissions, coordinated spatial use, and distributed MIMO. The first three ways are quite easy to be implemented, so it seems that they will be really supported by Wi-Fi 7. But as for distributed MIMO operation, it requires tight synchronization, it requires a very wide, very huge backhaul, and that's why there are some issues and there are some doubts that this technology will come to the standard. And finally, an important feature of Wi-Fi 7 is support of real-time applications. When we are talking about real-time applications, we mean that the data shall be delivered within a small delay budget with a very high reliability. And by talking about small delays, we mean not minimal delays, but we are talking about limited delays. So many applications like video streaming, gaming, and so far, they indeed do not require to have as small delay as possible. They require that their delays are limited by some threshold, and none of the packets is related to this threshold. The solutions which enable real-time support of real-time applications in Wi-Fi 7 are being discussed in the group. The main two directions are, so the first one is improving random access, improving traditional channel access methods that are used in Wi-Fi networks, is EDCA. And the second direction is based on periodic channel reservations, which is implemented with a target wait time mechanism at quiet time period. So TWT was introduced in .11ah to improve power save operation, but later it was changed to as just a tool for scheduling transmission. The next item is millimeter wave Wi-Fi, and millimeter wave Wi-Fi is already presented in into the spec. So the first spec supporting millimeter wave Wi-Fi was .11ad, which supported up to 8 gigabit per second data rates, and there are many use cases that require such high data rates, so even much more higher. Such use cases are networks in data centers, streaming a video from some devices to TV or displays in home, mobile front-hauling and backhauling for public networks, and so far. All these applications require very high delays, throughputs, and maybe even much more higher than 8 gigabit per second. So that's why the .11 working group improves Wi-Fi in order to have even higher data rates. So what was done in .11ay, the second generation of millimeter wave Wi-Fi? So .11ay is an extension of .11ad, improved by higher wider channels, 8 gigahertz bandwidth instead of 2 gigahertz bandwidth of .11ad, and also introducing MIMO in millimeter wave communications. .11ay supports up to 8 spatial streams, and together with higher bandwidth, it allows us to have up to 277 gigabit per second in theory. In reality, the data rates are smaller. For millimeter wave, we need a special sounding procedure, special beamforming, because traditional beamforming used in .11 AD had high overhead if you have multiple devices. And the final amendment, which improves data rates, and it uses not traditional bandwidth, not traditional spectrum, is .11bd, which focuses on light communications. So the use cases for light communications are as follows. So first of all, there are a lot of industrial applications where radio transmission is unstable because of a lot of reflections and so on. There are some medical environments. There are dense enterprise networks with access points deployed every 2 or 3 meters. So the network is really very dense, and we need to allow partial reuse operation, but we cannot do it with traditional radio frequencies. And also secure network, because if we have radio frequency, as anybody can listen to the channel and obtain, collect data which are transmitted, even if they're encrypted. So we have we may have some security issues. But with light communications, we have directional transmission, and it improves security. So at the very beginning, there was a very high interest to light communications, but then the work on .11b has started, and because of this, the interest to light communications went down, and now the development of 11bd is extremely slow. So the work should be finished by 2022, but it seems that the work will be extended for several more years. Right now, what we have 3 5 protocols in the specification that uses. So one of them is mandatory, but it has very low performance, and it is standardized only for coexistence of the other two files. So the channel bandwidth is quite small, and the MCSs are rather small because we use because this file uses a small coding rate and BPSK modulation. There are also 2 other modes, 5 modes. One of them is inherited from by 5.6 from .11ax. So it's just adaptation of .11ax to light spectrum. And another one is taken from E2T recommendation G9991, and it's really very so this PHY is really very so it takes into account all peculiarities of light spectrum, and it optimizes the usage of wide spectrum. One of the interesting feature of this PHY is adaptive bit loading, and it works in the following way. So in Wi-Fi networks, when we transmit some data in some wide channel, we use the same data rates as the same modulation coding scheme at all frequencies. But in light spectrum, we have the following problems. So different frequencies have different attenuation, and that's why sometimes we need to and moreover, this pattern can be rather static, and it means that we can improve performance by introducing adaptive bit loading, meaning that every tone here may have a different modulation encoding scheme. And this, depending on the signal-to-noise ratio, and this significantly improves performance. So there are a lot of studies. So this is like a very there are a lot of studies related to this specification, and that's why .11 wants to incorporate it in Li-Fi. And the final specification that improves data rates is next generation V2X. So this specification is somewhere in between those ones that improve data rates and those ones that provide new services, because actually the data rates are not so high here, but this specification is an improvement of .11p. .11p is a special amendment of Wi-Fi standard special technology that operates in 10 megahertz and brings Wi-Fi to the market of V2X applications. So it was developed many years ago, and now the performance of .11p is very small with respect to the requirements. So that's why .11bd improves the performance of .11p by extending the bandwidth, by introducing better coding schemes, improving reliability and range in the fast-changing radio frequency environments. It introduces new modulation coding schemes and introduces MIMO to V2X communications. So the data rates that are available in this next generation V2X are as high as 180 megabit per second. Of course, these data rates are very small if we compare them to like traditional Wi-Fi systems, but for V2X applications, it's very difficult to obtain high data rates. So that's all about the amendments which improve data rates. And if you have questions, please let me know. Now let's go to the amendments which introduce new services. And these amendments are really very interesting because typically the presence of these amendments is hidden from the end customers, and but actually these amendments are very important. So .11b is done for extremely low power operation. Low power Wi-Fi systems are very important because when we use Wi-Fi, our batteries of our smartphones ends quite quickly. So that's why there are a lot of efforts towards improving power consumption of Wi-Fi systems. And 11b traditionally power management in Wi-Fi networks is done in the following way. So we just from time to time, we just switch off our radio. But when we switch off our radio, we cannot transmit or receive data. So if the radio of a smartphone is switched off, the smartphone cannot receive some data. So it can, there are delays in transmitting data to the smartphone, because first of all, smartphone needs to switch on its radio. Then after that, it needs to check whether it has some buffer data or not. And .11ba changed the paradigm of how power management works in Wi-Fi. It introduces wake-up radio, low power wake-up radio. So with .11b, we have two radios in Wi-Fi. A Wi-Fi device has two radios. One is called PCR, or primary connectivity radio, and this radio is used for data transmission. And another one is quite simple and is used only to wake up a smartphone. So it's quite simple. It consumes only microwatts or milliwatts, and so it's less expensive from the power consumption point of view to use this radio. So how power management is organized typically? So we have this, so the primary radio can be switched off for a long time, but this wake-up radio can alternate between the on and off states. And when it is on, it can check whether there are some data buffered for the smartphone, for the PCR. If there is no data, so this radio just switches off, and that's all. If there are some data, the primary radio is switched on and it retrieves this data. So this wake-up radio, low power wake-up radio, is not used to get some data, to transmit some data. It's only used to improve power management. And indeed, so we have done some research related to this technology, and we can confirm this indeed this technology significantly improves power efficiency of Wi-Fi networks. The next amendment is .11az. It introduced next generation positioning. So Wi-Fi today is not used only for data transmission. It is also used for many other services. So one of them is positioning of the devices. We have a lot of use cases that require positioning. For example, micro-location in store, positioning for home audio, like we can have systems that support follow me sound, or we can have advanced audio systems that require self-calibration. We can use navigation at public buildings or at massive events. We can use positioning to improve network management, for example, to decide to which access point a device needs to be connected. We may have many medical tracking applications that requires to understand where is the person. We may have so positioning can improve experience of video cameras because it allows us to track moving people in a more simple way. Positioning is very useful for UAVs, and it allows us to introduce such services as follow me mode. Wi-Fi based positioning can be used for in underground mining or for pipe vault robot positioning and so far. And all these use cases require rather high accuracy in positioning, sometimes up to 10 centimeters. For example, micro-locations draw on some medical tracking applications or so far. And if we looked in how positioning is supported in .11, we can see that from the very beginning there were several approaches of supporting positioning. So the first approaches were based on RSSI, so the signal strength, and the accuracy of these approaches was too small. Then there were some approaches introduced to that were based on time of departure. So if a station transmits some frame, several neighboring access points can compare the time when this frame arrives at these access points. And based on these time shifts, they can understand what is the difference between what is the distance between the station and all these access points, and then to locate this station. There is also a fine timing measurement protocol introduced in .11 that provides accuracy as high as 1 or 2 meters. And for next generation positioning, we need we need high accuracy, as I previously said, about 10 centimeters. So to provide such type of accuracy, .11az introduced enhanced fine time measurement and improved angle of arrival or angle of departure estimation. Very important properties of these solutions are as follows. So they do not require association, and they have pre-association security negotiation. It means that we can obtain some service in a secure manner, but without being associated to multiple stations or to multiple access points, which is not supported by the standard. So .11az describes several ways to transmit frames used for positioning in case of multiple stations. So traditional DCA can be used, or trigger-based transmissions introduced in .11ax can also be used. And it describes several ways of sounding for positioning based on physical layers that are based on the signals that are introduced in Wi-Fi .11ac, .11ax, and millimeter wave Wi-Fi .11ad and .11ay. And I see questions. So, is positioning in .11az secure? Should we be afraid of being tracked at home or in some public places? Actually, this is a very good question. So from the security point of view, so first of all, so as it is shown here, so we indeed have some security negotiation. So we can say that the position .11a that is indeed secure. At least it is assumed by the standard developers. But I think that the question is not about the security, but about privacy. And as for privacy, I will talk 5 minutes later. So let's see, there are really very interesting ideas related to privacy of .11 networks, future .11 networks. So the work on .11az is almost finished. So there are no huge changes expected. But what is really a hot topic today is like the next generation of positioning. So what will be the next? And the next is the usage of Wi-Fi networks for various sensing applications. When we are talking about positioning, we try only to understand what are the coordinates of some device, some smartphone or some other type of device. When we are talking about sensing with Wi-Fi networks, it's very close to what is called radio vision. So we use Wi-Fi signals to understand the position or to understand the events that occur in some area. For example, we can use Wi-Fi signals to monitor whether there are some people in the room. We can use Wi-Fi signals to understand whether we need to switch on or switch off light or heat or something else. We can use Wi-Fi signals to understand whether a person is staying or it falls down, and it's very important for elder care. We can use Wi-Fi signals to remote operator for remote operator troubleshooting, for recon approach or lock on walk away, for gesture recognition, and for capture some biometric data. In all this, so there are a lot of papers which study various applications of Wi-Fi sensing, but Wi-Fi sensing is not supported by the standards, so its capabilities are quite limited. Sometimes we can, for some applications, we can modify the standard to improve performance. And the sense task group is the group which tries, so this is .11pf. And this task group tries to understand which changes need to be done in the Wi-Fi protocol to improve all these sensing applications. So the work on in this direction has started quite recently. So we do not have any approved draft. We do not have any even draft specification. We have only some ideas which are currently discussed in the task group. So everybody can provide his own ideas and can contribute to the development of this specification. And the final part will be about random and changing MAC addresses for privacy. So this again, so this is what Ilya has asked. So what about privacy? So in Wi-Fi currently we have these services like sensing, like positioning, and what about privacy? Actually, the concerns of communications privacy are not new. Privacy was an important selling point for Dell phones in 1912, many years ago, more than 100 years ago, because such kind of phones did not require an operator to make the call, so they provided privacy. Today, a lot of devices, so here this slide is about smartphones, but it's not only about smartphones. A lot of devices, they're really very talkative. And even when our smartphones are disconnected from some Wi-Fi network, they try active probing, they search for particular SSID, so they transmit some frames and they disclose the location of the users. Location plus time plus frequency plus MAC address reveal all your secrets. For example, we based on the information obtained from public Wi-Fi access points, we can say that, okay, this MAC address pops up at the clinic twice a week. Or this MAC address is near the liquor store at 8 a.m. every day. Or this MAC address leaves an apartment every morning at 10 o'clock. So all this information is very important, and it's quite straightforward to create personally identifiable information from this data. There are a lot of scandals in the world related to privacy. So all these privacy issues are real. For example, there is a scandal related to Transport for London. that it actually tracks all London Underground users with Wi-Fi. Similar systems works in Moscow, where the data gathered from public Wi-Fi access points can be used to track territorial bans, medical restrictions, and also loyalty. Again, related to London, in London there was a huge scandal several years ago when it appeared that London's trash cans tagged people that use smartphones. Similar scandals were in US. So all these issues are real. How we can change the situation? For example, we can use random MAC addresses. We can change a MAC address of the device every time when we associate to some access point, or even more frequently. But actually, random MAC addresses are not enough to save our privacy. We have a lot of other identifiers, and we need to remove them or change them together with the device address. We have some constant fields that describe, for example, the capability of devices. We have content-based fingerprinting. We have timing-based fingerprinting, and we can use some replay attacks. So there are really a lot of issues together with introducing random MAC addresses that need to be solved. And currently, these random MAC addresses are implemented by vendors, and a lot of also there are some recommendations like in .11 AQ that introduce some variable for privacy, and when this variable is set, station shall periodically randomize its MAC address. It shall do some more actions, but a lot of decisions are left for vendors, and this is very important because nobody knows how these vendors implement these crucial for privacy decisions. And that's why currently 2 new task groups start their work in .11, which focus on privacy. So one of these task group, .11BH, specifies modification to MAC to preserve the existing services that might otherwise be restricted environment where stations use randomized or changing MAC addresses without affecting user privacy. So this task group focuses on how changing MAC addresses or changing some other information affects the other services that are available in .11 networks. What shall be done what shall be changed into the specification to support randomize to support random MAC addresses. And another task group, .11BI, specifies modifications to MAC layer that address and improve user privacy. So this task group, so it will study and develops new solutions that improve privacy in .11 networks. So this finishes my talk on new amendments, new features that are under development in .11. From my talk, I think you have understood that there are several directions in improving Wi-Fi. So the first direction is high data rates and high performance in traditional understanding what it means. And these high data rates are supported both in traditional spectrum like 2.4, 5, or 6 gigahertz, and also for say some specific spectrum like light communication or millimeter waves. And the other group of amendments, they improve some functionality of Wi-Fi technology by reducing power consumption and by introducing new services that enrich the Wi-Fi technology. And Wi-Fi technology starts not only to transmit data, but also to provide some services which are not related to data transmission. Thank you for your attention. If you have questions, I would like to answer them. And I see one question in the chart. How sensing is to be realized? Is it involve both IP and client like downlink coupling, created channel monitoring, or only one side devices is enough? So there are several approaches how to implement sensing. And of course, for very fine, for very high accuracy, we need both access point and station involved in these communications. But in reality, so some approaches like this one, it does not require that the station support these new features, because what we can do, we can just get time when some frames arrive at neighboring access points, and then calculate the difference in the distances between this station and these access points. And after that, we will understand the position of the station. Moreover, we can understand the direction, so the angle of arrival. When the station transmits some sounding frames, these sounding frames, for example, can be transmitted for mimers. So starting from dot 11, and there are some sounding frames, and so we can use some legacy frames to obtain the to estimate the coordinates of the devices. But of course, for very fine measurements, we need support of the protocol from both sides. Any other questions? Do you expect that the work on Wi-Fi in sub 1 GHz will be continued? It's an interesting question. So one of the reasons why there are no so many devices that support sub 1 gig communication is that when the standard was ready, the vendors put much efforts on .11ax, which is Wi-Fi 6, which works in traditional market, Wi-Fi market, and so the benefits of supporting this new Wi-Fi 6 technology were quite apparent, and so most efforts have been put on supporting this new technology, but not to .11a AH or Wi-Fi Hello, so sub 1 GHz communication. Interestingly, that a lot of solutions that were developed for sub 1 GHz communications are now incorporated in 2.4 and 6 GHz communication. So in traditional spectrum like TWT or some other solutions. Why it happens? It happens because I think that the community decided to improve, instead of developing a separate technology for IoT applications, but if we are talking about sub 1 GHz communications, we need to understand that the access point. So this technology is not compatible with traditional Wi-Fi. So it requires new access points, requires new devices. But if we are talking about traditional spectrum, so devices are backward compatible. And instead of developing some new technology which is not backward compatible, the community tried to adopt the traditional technology and even .11ax or .11ay, sometimes consider use cases that are typical for IoT communications for which .11aah has been developed. So I think that the features and the mechanisms that the most important, the most efficient mechanisms that were introduced in .11ah, sooner or later, then they will be incorporated into 2.4, 5, or 6 GHz communications. We see some evidence of this related with the. We see some evidence on of this today. For example, TWT, target wake time, which was initially designed in .11ax, then it was incorporated. .11ah, then it was incorporated and a bit modified in .11ax as a power management technique. But now it is used in .11be for providing real-time for providing support for real-time applications. Any other questions? Am I right that .11az is an extension of .11ay and .11z doesn't specify the exact way of angle of arrival estimation? So first of all, .11az is not an extension of .11ay. I would say that .11az is an extension of many PHYs, of many PHY layers that are already present, that are already in the standard. So it extends not only .11ay but also .11ax, .11ac, and many others. So it improves the file layer by introducing some features that enables fine positioning. And as for angle of arrival estimation, so the standard describes the ways how to transmit sounding frames that can be used for angle of arrival estimation. Of course, so as for the exact algorithm, how to do and what shall be done, so it's implementation dependent, but the tool, the signals, the frames, so they're specified in the standard. Unfortunately, so you can see here that for many amendments, I tried to find some papers which provide some general overview for this amendment. Some of them are ours papers, so wrote in our lab. Some of them are papers written by other scientists, but for .11, AZ, I didn't manage to find some good, really very good overview that can provide some good vision on this technology. But the standard is not too heavy to read, so it incorporates many techniques. So I think that one of the next seminars can be related to .11 AZ amendment, because it's quite interesting here.
Thank you, Evgeny, for your presentations. I guess if somebody has questions in Russian, he can ask it now. Okay, I guess there is no questions left. So thank you, Evgeny, for your good lecture, and it was very interesting. And do you have some announce about second part of your presentation?
Yeah, so thank you, Vyacheslav. So actually, we have one more question. Which frequency band are expected to be used for sensing traditional 1 millimeter waves? I would say that both. So of course, millimeter wave, the usage of millimeter wave communication, millimeter wave frequencies can provide high accuracy because we have short wavelengths, and so it's better. Yeah, but I think that both traditional spectrum and millimeter wave will be used for sensing. And as for future talks, so I think that in several weeks we'll have talk on Wi-Fi 6, and after that we'll have talk on Wi-Fi 7 and maybe some other Wi-Fi technologies. So if you have some requests, so please share them, and me or my colleagues will make a talk on these technologies.
Thank you. The next seminar, the next Moscow telecommunication seminar will be held on next Tuesday. It will be devoted for cellular networks, and Artem Krasilov will be a speaker, and he will tell us about URLC enhancements in latest 3GPP releases. So we will be happy if you visit us next Tuesday also. Thank you.